Welcome everyone. I am Maria Vincent, Assistant Professor, Department of Electronics and Communication Engineering, Rajagiri School of Engineering and Technology. Today I will be discussing on the topic conventional AM or double sideband full carrier generation, which comes under the course Electronics Communication for S7 EE students. So in this lecture we are going to detailing the concept AM modulating circuit. So the AM modulating circuit can be classified as two, that is a low level modulator and a high level modulator. So the location in a transmitter where the modulation occur determines whether the circuit is a low level modulator or a high level modulator. So with the low level modulation, the modulation take place prior to the output element of the final stage of the transmitter. In other words, that is, it is prior to the collector of the output transmitter. Because of that reason, it requires very less modulating signal power in order to achieve a very high percentage of modulation. And one of the drawback of this low level modulator is it require very high power amplification before the transmission of the signal. And with the high level modulator, the modulation take place in the final element of the transmitter. In other words, we can say the modulation take place at the collector of the final transistor. So when compared with the lower level modulator, in case of high level modulator, it requires very high modulating signal power in order to achieve a very high percentage of modulation. So it required a very less power amplification before the transmission of the signal. So in case of low level modulator, it require very less modulating signal power, but in case of high level modulator, the modulation has take place in the final element of the transmitter, so that it requires very high modulating signal power in order to achieve a reasonable percentage of modulation. So in this slide we want to discuss the operation of a low level AM modulator. So this low level AM modulator is also known as emitter modulator. So this circuit is a small signal class A amplifier. So in the previous lecture we discussed that the amplitude modulation requires the two different inputs, that is a carrier and the modulating signal. Similarly, in this AM modulator, this amplifier circuit has two input, that is a carrier signal and the modulating signal. So the carrier signal is given to the base of this transistor, and the modulating signal or the message signal is given to the emitter of this transistor Q1. And this low level AM modulation is also known as emitter modulation because the modulating signal is applied to the emitter of the transistor. So low level modulator means if the modulation is take place prior to the output element of the transistor, then it is known as low level. So here the modulation is take place prior to the output elements. The output element is the collector. If the modulation is take place at the collector, then we can say it is a high level. But in this circuit, the modulation is take place prior to the output element, that is the modulation is take place at the emitter. That is why this is known as the low level AM modulator. So for the circuit operation, we have to consider two different cases. Case 1, without modulating signal. So if you are not giving any modulating signal at the emitter of this transistor Q1, then the circuit will act as a linear class A amplifier. That is simply it will amplify your carrier signal and it will be available at this load resistor RL. So the output voltage at this load resistor will be the carrier amplified by the amplifier voltage gain. And case 2, that is when modulating signal is applied. So in this case we have to apply both the carrier as well as the modulating signal to this transistor Q1. In that case, this amplifier is operate as a non-linearly, that is the modulating signal starts varies with the gain of the amplifier at a sinusoidal rate equal to the frequency of the modulating signal. So the depth of the modulation or the modulation index achieved is proportional to the amplitude of this modulating signal. So in the previous lecture we already discussed what is modulation index, that is M is equal to EM by EC. So in the circuit, in the low level AM modulator, this depth of modulation or the modulation index achieved is proportional to the amplitude of the modulating signal, and the voltage gain of this transistor is of this emitter modulator is expressed as AV is equal to AQ into 1 plus M into sine 2 pi FM into T, where AV is equal to the amplifier voltage gain and AQ represents the amplifier quiescent voltage gain, that is without modulation. So the voltage gain for an emitter modulator is expressed as AV is equal to AQ into 1 plus M into sine 2 pi FM into T. So where M is equal to EM by EC, where EM is the amplitude of the modulating signal and EC is the amplitude of the carrier signal, and sine 2 pi FMT, where FM is the frequency of this modulating signal. And this sine 2 pi FM into T varies from plus 1 to minus 1. Hence the equation can be modified to AV is equal to AQ into 1 plus or minus M. So at 100% of modulation, M is equal to 1, and thus the equation changes to AV max. That is at M is equal to 1, this equation has become AQ into 1 plus 1, that is equal to 2 times AQ. So at 0% of modulation, that is when M is equal to 0, your sine 2 pi FM into T is goes to minus 1. So this expression has become AQ into 1 minus 1. So this term becomes 0. So the A minimum is equal to 0. So in this waveform, the modulating signal is applied. This modulating signal is applied to the emitter of the transistor, and the carrier is applied directly to the base of the circuit. So the modulating signal drives the circuit into both the saturation and the cutoff, thus producing the non-linear amplification necessary for the modulation to occur. So the collector waveform includes the carrier and the upper and lower sideband frequencies as well as the component at the modulating signal frequency. So the coupling capacitor C2 at the output of the transistor removes the modulating signal frequency from this AM waveform, thus producing a symmetrical AM envelope at the load resistor. So at the circuit, after that collector, we are having a coupling capacitor C2 which can remove the modulating signal frequency, hence it can produce a symmetrically AM envelope at the output. So with emitter modulation, the amplitude of the output signal depends on the amplitude of the input carrier and the voltage gain of the amplifier. So the coefficient of modulation depends entirely on the amplitude of this modulating signal. Then we'll move to the drawback. So one of the drawback is it is operate in a class A configuration, so it is extremely inefficient. So the class A amplifier is extremely inefficient. So this low level modulator, that transistor Q1 is operate in a class A amplifier, which is extremely an inefficient amplifier. And the another one, it is incapable of producing high power output waveforms. Since it is a low level AM modulator, the modulation is take place prior to the output element, so it require very less modulating signal power. So at the output it is producing very low output power waveform. That is one of the drawback. So in this slide we are going to discuss high level modulator, which is also known as collector modulator. So this circuit has a small signal class C amplifier, and this amplifier has two inputs, that is a carrier signal and the modulating signal. And this high level modulator is also known as collector modulation, because the modulating signal is applied directly to the collector of the transistor. So in this circuit we are giving the carrier signal to the base of the transistor Q1, and the modulating signal is given to the final stage of the transistor, that is to the collector of the transistor Q1. Hence the modulation is take place at the final stage. That is why it is known as the high level modulator or collector modulator. And in this circuit you can see an RFC, that is a radio frequency choke, which isolates the DC power from the high frequency carrier signal. And in the circuit it is clear that the unmodulated carrier is given to the transistor Q1. So this unmodulated carrier will control the turn on and off position of this transistor Q1. So we already know that in order to switch on this transistor, this carrier amplitude should exceed the barrier potential of this Q1. So if it is a silicon transistor, the barrier potential will be 0.7. So the carrier amplitude should exceed that barrier potential, then this transistor Q1 turns on. So if the carrier amplitude drops below the barrier potential, then this transistor Q1 turns off. So the turn on and off position will be controlled by this unmodulated carrier signal. So the operation, the circuit operation will explained with the help of two cases. The case 1 with no modulating signal. So in this case we are not giving the modulating signal at the collector of the circuit. We are having only the carrier signal, which is given to the base of the transistor. So when the amplitude of the carrier exceeds the barrier potential, already told, for a silicon transistor that barrier potential is 0.7, and if you are using a germanium transistor, that barrier potential is 0.3. So if the amplitude of the carrier exceeds this barrier potential, this Q1 turns on and the collector current flows, and when the amplitude of the carrier drops below 0.7 volt, then the Q1 turns off and collector current drops. Means it will stops. So the figure shows the operation of this case. So here it given the carrier signal. So when the carrier amplitude exceeds this barrier potential 0.7, then Q1 turns on. If the Q1 turns on, then there will be some base current. So because of that base current, there will be some collector current. And this transistor will turns off when the amplitude of the carrier drops below this barrier potential. So from this point, the collector current, the base current will be 0. If IB is 0, then collector current will be 0. So during the next cycle, when the carrier amplitude exceeds that barrier potential, your transistor turns on. Then there will be some base current. Because of that base current, there will be some collector current. So because of this collector current, at the output we are having some output voltage. So because of that, your Q1 will switches between saturation and the cutoff, which is controlled by the carrier signal which is given to the base of the transistor, and the collector current flows for less than 180 degree of each carrier cycle, and class C operation is achieved. So at the output, your output waveform will be shifted 180 degree. So this is what the case 1. In case 1, we are not giving a modulating signal at the collector. We are having only the emitter. We are giving only the carrier signal at the emitter, and that carrier signal will control the turn on and off position of the transistor. If the transistor is turned on, then there will be some IB. Because of that IB, there will be some IC. So if there is some IC, at the output you are having the output voltage. So when the barrier potential, if the amplitude of the carrier drops below the barrier potential, then the transistor Q1 turns off. Then your IB will be 0. If IB is 0, your collector current is 0, then your output will be what? The output will be VCC. So this is what. And in case 2, you are giving the modulating signal. So in this case, in the circuit, we are having the two input, that is the modulating signal and the high frequency carrier signal. So the transistor Q1 turns on if the amplitude of the carrier exceeds the barrier potential of the transistor. So there will be some IC. Because of that, there will be some output. So if you are giving along with that, if you are giving the modulating signal to the collector in series with the DC supply voltage, it adds to and subtract from the VCC, causing the amplitude of current pulses through the transistor Q1 to vary. So as a result, the amplitude of the carrier sine wave varies in accordance with the modulating signal. So it can be seen that the output voltage waveform swings from a maximum value of 2 VCC to approximately the VC set, that is 0 volt. So in this case, if you are giving a carrier signal to the base of the transistor, your transistor will turn on. There will be some IB. Because of that IB, there will be some IC. So if you are giving the modulating signal, this IC will vary in accordance with the shape of your modulating signal. So because of that, your collector current is also varies. So because of that, there will be some change in the output voltage. In this slide, we are going to discuss the limitation of conventional AM or double sideband full carrier. So in conventional AM, only 33.33% is the maximum efficiency that can be achieved. That is, the maximum power that can be carried by the sideband is only 33.33%. So in case of conventional AM or double sideband full carrier, you are having 3 signal component, that is a carrier and a upper sideband and a lower sideband. So the carrier signal is just a high frequency signal which is used to carry the 2 sidebands, and most of the information is occupied within this 2 sideband. So the maximum efficiency that can be achieved in case of conventional AM is only 33.33%. So most of the power transmitted in conventional AM is occupied by the carrier. So most of the power is wasted for transmitting the carrier signal. So what is the solution to this problem? The solution is, when the carrier is suppressed, the total power is equal to the sideband power. So the 100% efficiency can be reached. So this is called as double sideband suppressed carrier modulation. So if we are able to suppress the carrier and if we are able to transmit the both sidebands, then the efficiency can be achieved as 100%. So the practical significance of double sideband modulation is the reduction in transmission power required to cover the same area. So the reduction in transmission power reduces the amount required for the equipments. So next is the application of AM. The amplitude modulation is used in a variety of applications. The first one is it can broadcast the transmissions. That is, the AM is still widely used for broadcasting on the long, medium and short wave bands. It is simply to demodulate, and this means that the radio receivers are capable of demodulating. The amplitude modulation are cheap and simple to manufacture. So if you are using AM, then the modulation and the demodulation procedure is quite cheap and simple. Next application, that is air band radio. So the very high frequency, that is VHF transmission for many airborne applications still using this AM. It is used for the ground to air radio communication as well as the two-way radio link for the ground staff as well. And the third one, that is single sideband. The single sideband concept we will discuss in the next lecture. So the single sideband means the amplitude modulation in the form of single sideband is still used for the high frequency radio link. So in case of single sideband, we are transmitting either upper sideband or lower sideband, so that we can reduce the bandwidth. So which is still using for the high frequency radio links. Then next is the quadrature amplitude modulation. The AM is widely used for the transmission of data in everything from short range wireless link such as Wi-Fi to cellular telecommunications and much more. So with the help of this quadrature amplitude modulation, we are able to transmit the data over the wireless links such as Wi-Fi to cellular telecommunication and much more. So in this lecture, we discussed the AM modulating circuits, that is low level and high level modulator, which is used to generate the conventional AM signal. So in the conventional AM signal, one of the drawback is the maximum efficiency which can be achieved is only 33.33%. So if you want to improve your efficiency from 33.33 to 100%, then we have to suppress the carrier. So the carrier is only a high frequency signal which is used to carry your information signal. So if you are able to suppress the carrier signal, then the 100% efficiency can be achieved. Then we found a different application of AM, that is broadcast transmission, air band radio, then single sideband and quadrature amplification. So in the next lecture, we are going to discuss the double sideband suppressed carrier and single sideband AM. Thank you.